Well, hello everybody, it's Dave, and today we're going to culminate an entire course worth of work in statistics with this idea of significance testing. So hopefully you remember things like the normal distribution, p-values, experimental design, how to satisfy conditions, and their importance to the idea of the sampling distribution. Now in previous work, we played around with this idea called the confidence interval. And the goal of a confidence interval was actually to estimate the population parameter. However, what if we have a population parameter and then we observe another value and we notice that there's a difference between the two? Is this difference statistically significant, and does it make us question whether our parameter is the true parameter or if it will need adjusting? When you start to have this conversation, you are now in a significance test environment. And let's show you an example to help you understand what I mean. There's an online applet called the Great Free Throw Shooter. And let's say that there's a basketball player that claims that they make 80% of their free throw shots. And we run the applet a few times and we notice that the player is actually making less than 80% of their shots. Well, does that mean that the person was exaggerating and that their understanding of their average was wrong? Or is our value not so far away that it is deemed significant? And so we've already started the first and one of the most important parts of significance testing in this idea of the hypotheses. Now, within a significance test, there's two hypotheses that have to be made. The first is the statement that the parameter is what we thought it was. In this case, it would be 0.8. Well, if there is no difference in the parameter, we call this the null hypothesis, which is labeled with H naught. On the other hand, if our observation gives us evidence to suggest that there is a difference in population parameter, we call this hypothesis the alternative hypothesis or the alternate hypothesis. And this is always labeled with an H subscript A. And so for our scenario, we would look at something like this, that the null hypothesis is the fact that P is equal to 0.8, and the alternate is equal to P being less than 0.8. Now you'll notice that there's a colon in between H naught, HA, and the statements of P equal and P less than. That's because the null hypothesis is not equal to 0.8. The parameter P is equal to 0.8. So you have to make sure that you list these like this. It seems like a nitpicky thing, but it's a really important statement because this means something different than if you just said H naught was equal to 0.8. That's a big no-no. There are three scenarios that we have to consider when we're talking about the alternate hypothesis. The null hypothesis is always going to be the parameter is equal to whatever value is stated. But when we're talking about the alternate, there's really only three scenarios to consider. It's either going to be less than the value because the person is exaggerating, or it's going to be greater than the value because the person was underestimating, or we just don't know which way it's going to go. So in that case, we just state that the parameter is not equal to whatever value has been stated. And so the language in the question is going to be very vital for this because based upon which hypothesis we have to state, that's going to change the calculation that we do later on down the road. And so when we're referring to either something being less than the value or greater than the value, we're referring to a one-sided test. However, if we don't know whether it's greater than or less than, then we have to consider both sides of the distribution, which means that it could either be less than or greater than, which we just state as not equal to. So it's important to read into the question effectively to be able to glean this out. It's one of the most common mistakes that's made. Now, one of the more nitpicky parts, but again, it's essential when you read this because when you look at AP problems or statistics problems in general, you're going to see that there's a lot of things labeled with Greek letters and scripted letters, and there's going to be a lot of things labeled what I call decorated letters like hats and bars and things like that. We never, ever, 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 ever label a hypothesis in terms of the sample. So in this case, P hat or X bar. It's always related to the population parameter of interest. So please make sure that you take a look at the language of the question before you make that statement. The other idea too is a lot of people like to reverse engineer problems to come up with the answer before they even know how to start the question. In practice, it's actually the other way around. You should always be making hypotheses before you actually have the data to make the final conclusion. Again, we're making a claim against the population parameter. So let's go back to the basketball example, and let's go and use that applet, and say we make a set of 50 free throws and the person actually makes 32 of them. Well, a sample proportion will tell us that that's only 32 out of 50, which is 0.64. Well, that's not very close to 0.8, but the question is, statistically speaking, is that significant? Well, there are many ways we can go about this, but one of the most straightforward ways is to actually simulate this a whole bunch of times. Hopefully, from your previous work in probability, you know that if we randomly generate values based upon this reality that the proportion is 0.8, we should end up with a normal distribution looking scenario centered on 0.8. And so when we do this, sure enough, we end up with this normally distributed looking dot plot. But you'll notice at the very left tail, there's only 3 dots that are either 0.64 or less, which means that there's only 3 dots out of 400 that are the same value as our observation or lower, which gives us a probability of getting this value to be 0.0075. Now notice with all of our calculations and all of our values, we're still dealing with proportions. Make sure that you take percentages and convert them into proportions. So what does this actually mean then? If we thought that the population parameter was 0.8, but our observation of 0.64 is so rare that there's only 3 out of 400 simulated occurrences of it occurring, well, there's only 2 conclusions that we can make. The first conclusion is, yep, the null hypothesis was right all along. And this is just a very unlikely outcome, and there was 3 out of a possible 400, but it's still possible, therefore the null is right. But the other scenario is, well, hold on. What if the population proportion is actually less than 0.8? So much less that it would make our sample result not an unlikely outcome. Well, when that's the case, we're getting into this idea of statistical significance. You'll remember back in the day when we talked about significance, we referred to it in terms of being so far away from the mean or from the proportion that it could not have happened by chance. Well, when we're talking about it in terms of hypotheses, we use exactly the same language. It would rarely happen if the null hypothesis were true, is good evidence that the null hypothesis is not true. So we go back to this 3 out of 400 value, and we say to ourselves, what does this actually mean? Well, we calculated that there were 3 out of 400 cases that were either equal or less than the value that we had according to the simulation. And it was a very small number, which means there's only, in our simulation, 3 observations that are of equal or lesser value than what we have. Compare that to a simulation that maybe ends up with 80 dots that are less than or equal to what we have. That means that there's a lot more situations where there are values that are going to be farther away from the parameter given that h0 is actually going to be true. And so when we're interpreting this p-value, what we're asking ourselves is it so small that there are so few possible observations that could be farther away than ours that we have to state that it's statistically significant, versus the idea of it's kind of far away, but there are so many other points that are even farther away that this one doesn't seem so statistically significant. And so we've dealt with this idea of statistical significance before, and it is the exact same argument now. So when we have our statement, we have this p-value of 0.0075, which is really small, which means that our observation is so far away that it couldn't have happened by chance. Well, there's only one of 2 answers that we can now give. We're either statistically significant so that we reject the null hypothesis that p is equal to 0.8, or we don't have evidence to suggest that the null hypothesis is wrong, which means we fail to reject the null hypothesis. Now, it's really important that when you write these questions out, especially with this statement, you absolutely never use the idea that we accept the null hypothesis. We are not in the business of proving that the null hypothesis is true. We are making statements based upon our observation and suggesting that if the null hypothesis were true, what is the probability that our observation could have other values that are even farther away from it? So in a nutshell, when you're doing a significance test, we state the null hypotheses. There will be conditions that we will have to satisfy at a later date to verify which test we're going to do. Then we're going to calculate the p-value, and then we're going to interpret that p-value and come up with a conclusion of whether we reject or fail to reject the null hypothesis. And in this blue box here, we can see that there's really only two scenarios. It's either the p-value is small, which means we reject it, or the p-value is large, which means we fail to reject. Now, this is a script that I want you to remember, that given that the p-value is less than a certain value, whether it's small or we give it a benchmark by which to measure it from, if we are going to reject the null hypothesis, that means that we have convincing evidence to suggest that our value of p is less than 0.8. On the other hand, if the p-value was much larger and we failed to reject the null hypothesis, that doesn't mean that we have proven it to be true. It just means we don't have enough convincing evidence to suggest that p is less than 0.8. So this is what we're talking about when we're dealing with significance testing, is taking these p-values, given the scenario of the question, and trying to make an inference based upon our statistical calculation. Now, some of you may not have liked the wishy-washy way in which we talked about it being small or large. Well, we also have this significance level value that we can use, and that's given by the Greek letter alpha. And alpha is going to be an important value to learn. We typically deal with the idea of 0.05 as the benchmark, where it's a black and white idea. If our p-value is less than alpha, then it's reject, and if it's greater than or equal to alpha, then we're going to fail to reject. I've been doing this a long time. I've never seen a p-value be right equal to the alpha value, so it should be an obvious difference between the alpha and the p-value for you to be able to make an appropriate inference based upon your values. So this significance level we're going to use in a later date in something called the power of a test, and it's a tricky little task, this power of a test, but we're going to figure out a way to apply this alpha value to that and hopefully make more sense of it as we move along. There's a problem with this. We're making statements on an imperfect mathematical principle. We're talking about best guess ideas, and we have this observation and we say, well, hold on, this observation is so far away that we don't think that the null hypothesis is actually true. But what if we found out in a later study that we were just flat out wrong, and we rejected the null hypothesis, but we find out later on that the null hypothesis was actually true? Well, when we have this scenario where there are additional studies taking place and there's more work being done to give us more values to actually make more educated inferences based upon our scenario, we're talking about a type of error occurrence. And this table right here, I would put a big star on it with any notes that you have to make sure that you memorize this table exclusively, because this is really the wrap-up of how types of power work. And the basic way to read this is the following. We do a sampling. We do a p-value. We reject the null hypothesis based on that p-value, but the null hypothesis ends up being true. We've made a type 1 error. Conversely, if we fail to reject the null hypothesis, but we find out that the null hypothesis is actually false, that's a type 2 error. In all other scenarios, it would make sense that we fail to reject and we find out that H0 is true. Well, that's exactly what we thought. Or we reject the null hypothesis and wouldn't you know it, later work tells us that the null hypothesis was false. That's the correct conclusion. So really what a type error is either reject to find out it's true or fail reject to find out that it was false to begin with. So this concludes our discussion of the basics of significance testing, this idea of What are we doing? Why are we doing it? How do we make an inference? What is this alpha value? How does it help us make an inference? And most importantly, what does it mean if we later on find out that our inference was actually flawed or right, depending upon what the future information tells us? So get busy with some of those problems. It'll make a lot more sense once you start working the problems. Next up, we'll be dealing with significance testing and dealing with proportions by themselves. Best of luck, everybody. We'll talk again.